Okay, so we just went over complements and supplements theorem. Let's go over the congruent complements and supplements theorem.
Okay.
This time again, it's on the other part of your yellow page, box in the theorem. This one's a little more complicated. I'm going to read it as my abbreviations say. Angles supplementary to the same angle or congruent angles are congruent. So I use the abbreviations there. But let's talk about it, and I really need you kind of thinking about what that means. So I want you to draw with me a 110 degree obtuse angle, and let's call it angle B, next to the supplements, the congruent supplements theorem. Draw with me a 110, please, approximately. Okay, the supplement to that, Holly, would equal how many degrees?
The supplement, it would be 70 degrees.
It would be 70. So let's draw angle A somewhere close to it. That would be about a 70 degree angle. Okay, we have supplementary angles. Let's draw another angle, angle C. Let's make it supplementary to the 110 also. Kyle, how many degrees would that one have to be?
To the 110?
Yes.
Have to be 70.
Okay, so angle C is over here also at 70 degrees. So what this theorem is saying is angles supplementary, that's A and C, angles supplementary to the same angle have to be congruent. Angles supplementary to the same angle have to be congruent. Y'all both picked the same number because that was the only number that added up to the 180. But that's what that's saying. So then ultimately angle A is congruent to angle C if they're both supplementary to angle B. Okay, same concept for the complements, the congruent complements theorem. Does that make sense? Vertical angle theorem, again, box it in. We have actually done this, written it down, but here it is in theorem form, and everything you're getting on these pages are all reasons to go into geometric proofs. Vertical angle theorem, remember if this is a 2x on this side and this is an x plus, let's think of my x plus 7 on this side, how can I make an equation because these angles are vertical, Skylar?
Since they're vertical, and you so you want to make them look like congruent?
Vertical
Just
angles
do
are congruent.
2x equals x plus 7.
So you would set up the equation 2x equals x plus 7. I should probably make a 7b out of that so that you could solve to find your value of your angle. Vertical angles are congruent, so you can use any equation to go with that. Right angle theorems. All right angles are congruent. So what do I know about right angles, Kyle? How many degrees?
90.
Okay, right angles equal 90, but if they are all right angles, then they are all going to equal 90, so they are all going to equal each other. So if you ever have in a proof, this is a right angle, this is a right angle, then automatically they are congruent to each other.
So x equals 70.
Yes, I just didn't finish that. If two angles are congruent and supplementary, then each angle has to be right angle, congruent, and supplementary, totaling 180, and then they have to be the same size. So 180 split in half. They also have to be a right angle or equal 90 degrees. Okay, we're going to add one more definition here. We've actually already done the definition, but it's about to be used in a proof. So definition, this is my abbreviation, DEFN. Definition of congruence. What does it mean to be congruent?
To be equal measurements.
Equal measurements,
Like
same
same
size,
limit.
same length, same shape, right? Okay, so that means that the congruent symbol and the equal symbol can really just be used interchangeably. So if you ever need to change from congruent to an equal sign or an equal sign to congruent, then you always will use the definition of congruence to do that. Segments and angles are usually listed as congruent things because they are shapes, but sometimes you will add them together, and to be able to add or subtract, you have to have an equal sign. So congruence to equals, this is just the reason you can change back and forth. All right, so let's take a look at your first geometric geometric proof, which should be the one that looks like this that you put in, the segment one. Okay, and then we're gonna fill in all of our reasons and statements. Remember, there's 5 parts to a geometric proof. You have your given statement. This should be a congruent symbol on there. Sorry, I'll fix that real quick. I couldn't type it. I know where to find it. The proof statement should also be a congruent symbol. And this is, so we have the given, the proof, the picture, the statement column, and the reason column. Very similar to the algebraic proofs we did last week, only with algebra, you're very used to seeing I'm subtracting, I'm adding, or whatever. With these, it's a little different. So we got to turn on the logic brain real quick. Okay. Turn on our visual because there is geometric with a picture. And let's think through the proof. Okay, before I start going through the steps of the proof, I want us to just think about what we're trying to prove anyway. So look at your segments with me. AB congruent to CD is given to me. I'll mark those. Even though they might not look congruent, that's what it's telling me. AB segment congruent to CD segment. Okay, I want to prove that AC and BD are the same. So this is what I'm trying to prove. AC, BD. All right, think about it with me. What if A, B, and CD are both 5 units long and BC's 2? How long would AC be? 7. 5 in the middle, 2 in the middle. 5 plus 2, 7. How long would BD?
7.
7 also, because I took the 5 and did what with the 2?
Added
Added it. And then it would show me that the lengths are the same because I've added the same amount to both pieces, right? So technically, that's what we're about to do in proof form, but without the numbers. Okay? So ready? What is the first thing we put into our proofs as of last week with the algebra ones?
Given.
The given, right. So you're going to take your given statement and just enter that right here. A, B, congruent to C, D. And because it is given, every statement has a reason. Okay, the only thing that changed from number 1 to number 2 is the congruent symbol went away and then it became an equal sign. We just wrote that down. What lets me go back and forth between them?
They're the same, basically.
Yes.
Wait.
The definition of
The thing you just
Can't
said.
turn the page.
The symmetric. No, that's not right.
we just wrote it down. Very last thing on that.
Definition of
Yeah.
congruent.
Definition of congruent.
Wow,
I
I
see
said-
that. Bless you.
Said it.
So the only thing that you can use this thing for, definition of congruence, is just to change from congruent to equal and equal to congruent. And that's what we did. Okay, then we get to number 3. Now you can look back on that page, Holly. What lets BC equal BC? Something equals itself. Do you remember which property? That is it. BC
Heck
congruent
yeah.
to BC. The little piece here added to AC and the little piece here added to CD, that's going to be the same amount. So reflexive property. And that's exactly what we're doing. We're taking A, B, and CD that are equal. Okay, y'all watch up here real quick. These are equal. These are equal. We're adding two equal things. What are we adding to them?
2.
These are equal. What are we adding to both sides?
The exact same thing.
The exact same thing. Which
BC.
property lets you add the same thing on both sides?
Addition property.
So that's what's happening. 2 equal things. I'm getting the same thing added on both sides. So I have the addition property that lets me do that. Okay, kind of like we did with the numbers 5 plus that 2. So this is at my 5 plus 2 part numerically. Okay, segment addition postulate. What does that look like? Well, so far I need to get AC and BD in here. I'm trying to get to that statement, but I don't have them. But segment addition, what can total AC?
BD.
AB plus BC.
There we go. So if you look back, that segment addition postulate simply says the little part plus the little part equals the whole, right? So AC, the whole, is made up of AB plus BC. Okay, that's segment addition. That's all we're doing is just renaming that.
Wait,
Okay, but we also need BD.
then why did you add BC to AB and BC to CD?
I'm gonna get to that part. We're gonna use that in just a second. Okay, so back from the beginning, you have two congruent parts, which are two equal parts, and we added the same amount on both sides to those equal parts. All right, so we kind of have 7 and 7 right now, but we don't have any A, C, and BD up there yet. So we have to get that AC. The only way I know to get it is to take AC and add those two pieces. So BD, which two pieces are going to add to equal that? CD and
Yeah.
BC, right, are going to add to make that piece. Okay, so here's where it might get a little confusing, but I'm going to kind of use highlighters and different colors to show you. I knew these things were already equal right here. Look, they're also right here. AB plus BC, AB plus BC, BC plus CD, BC plus CD. Same things, right? Because these are equal, what could I replace them with?
The other things that are equal to them.
Since these are equal, I could put this in this one's place and this in this one's place. And so AC equals BD. So what is this reason for what I did right here? If I replace something.
The substitution.
That is correct. You're putting something in for something else. So the values that went in for these things, I substituted. Substitution. And then since they were equal, but I'm trying to prove congruent, I'm just going to go backwards and turn those back into congruent symbols. Why?
Because they're the same thing. The definition of congruency.
Definition of congruence. Okay, there is your first geometric proof. So there's no numbers really in it. It's all letters and proving by shapes. I don't think we have time to do the other one. It's basically doing the same thing but with angles. So what I would like for you to do is stop the recording for a second.